the Horner-Emmons reaction. A lot of similarities, but a little bit of a difference is that in our reagent, we have what's here known as a phosphonate ester. So this is going to take the place of the Wittig reagent. Still phosphorus, but not PPH3. Instead, it's this phosphonate ester. This proton over here now ends up being relatively acidic because if we were to deprotonate here, we could draw resonance structures with the phosphorus. So let's put one of the two hydrogens that's there. Now we can use something like this sodium hydride and a plus H minus, which is it's a weaker base than the N-butyl lithium, but it still acts as a base. So what this is going to do is take this proton off, put these electrons onto this carbon. All this stuff is the same. And now we've generated this species here. This now is going to react in a Wittig type reaction, or the Horner-Emmons reaction here. Notice it's not an ylide because it only has a negative formal charge. So this ends up being less reactive than that actual Wittig reagent, but still reactive enough to participate in a reaction. So let's go ahead and react this with something. Let's redraw this down here. How should I do this? I'm going to put the phosphorus up here. And then here's our carbon, here's our benzene ring. Or at least part of it. Like this. Move these two ethyl groups over here. So what I'm doing is I'm kind of flipping around that reagent. So now what we can do is let's have this attack some sort of an aldehyde or ketone. Let's just use an aldehyde this time. And let's just put a methyl group over here. So now we can use the same sort of reaction mechanism that we saw with the Wittig reagent. Let's have this nucleophilic carbon attack the carbonyl group. Even though this phosphorus doesn't have a positive formal charge, we can still have these electrons form a bond with the phosphorus and move these electrons up onto this oxygen. And actually, sorry, let's go through this stepwise, the way this is thought. This one is actually thought to actually happen probably in stepwise. We'll just draw all the steps out. So let's just first form our carbon-carbon bond. We can use this to illustrate something else. Oops, we lost the carbon here. Start over. So here's our benzene ring dangling down below. Now what we're doing is we're forming a bond with this carbon. We'll just put the carbon there. To emphasize, let's assume nothing else has happened here yet. So we can see both versions of this. Now, if we end up just having this carbon attack, this particular carbon here with not anything else happening, we have too many bonds to that carbon. So let's move these electrons up onto this oxygen. So now we're going to have something that looks like this. And now if we were to draw this stepwise, we would end up having these electrons attack this phosphorus, which is now neutral, but we can move these electrons up onto this oxygen. So this is very similar to our carbonyl chemistry. Rather than C double bond O, it's P double bond O. So now we need to rewrite everything here. We're forming a new bond between that phosphorus and that oxygen. All this stuff is the same. O ethyl here, O ethyl here, and now O minus. now what we can do is we want to generate our final carbon-carbon double bond. So we're going to break the phosphorus-oxygen bond, just like what we saw before. Break the carbon-phosphorus bond here. Form our final product that we're interested in. So let's put the carbon here. Just draw this out. C and CH3. And then on the bottom side here, this particular carbon, we have the benzene ring, and then there's a hydrogen that's not shown. So we'll have our, benzene ring and the hydrogen. And let's put the other species up here to get it out of the way. We'll end up having O minus, and I put the plus sign in the way. To slide down just a little bit, because now, as I've drawn here, this particular alkene also can have stereoisomers, because we have hydrogens here on opposite of each other, so this would end up being the E, because this is the higher priority, and this is the higher priority. Let's just flip the bottom around. I'll continue drawing that C just to emphasize that spot. The benzene ring over here. Hydrogen on this side. That's the E, it's the Z to help us stand out. And one important detail here, let's make this a little bit smaller so you can see everything. With the Wittig reaction, the first one, you end up with a mixture of E and Z generally. With this variation, this Horner-Emmons reaction here, I actually intentionally drew all of these as equilibrium arrows. Kind of snuck in an equilibrium arrow in each spot. Here, this reaction with this weaker species, not an ylid, but this phosphonate ester that you start with, allows the reaction steps to be in equilibrium, and you generally are going to form the more stable product in here. There's another stereochemical argument that we're not going to go into, but why this reaction is useful is that in this particular case, usually the E product is the major product. So this gives you more control over the reaction. So the original variation was the Wittig reaction, where you generally get a mixture. There's ways to affect the mixture, but it's still a combination of both. With the Horner-Emmons reaction, you can oftentimes have the E product be the major product, and be the major product to a significant extent. So it's not like it's 55 versus 45%, but much more major. So the major product. So if you're interested, we won't go through it because of the time and everything, but there's an interesting reaction to make the phosphonate ester here, which is known as the Arbuzov reaction. And it's in the textbook if you want to take a look at it. It's a SN2 reaction, like what we've seen before.